Chapter 7 all deals with work and kinetic energy. And here we have a picture of a car on an incline, and it's showing all the forces. For example, the force of friction. This would be the applied force of the car. We also have some air resistance, the normal force or the support force, and then this would be the weight. And we can see on this particular diagram that because the weight is straight down, it's also going to have a horizontal part and a vertical part using sine and cosine. Alright, work is only done when a force causes an object to move some distance. In other words, the object has to move, and the other stipulation in order to do work, that part of that force has to be in the same direction as the motion. And the equation that we use for work is W, which is for work, equals force times distance. And the SI unit that we're going to use for work is going to be newtons, because that's your force, times distance for meters, so Newton meter, or simplified as a joule. And in this particular picture, we can see this box has moved some distance, and the force that's being applied is in the same direction as the distance. So that means if we were to carry a box, we wouldn't actually be doing any work on the box, because our force would be up and the object would be moving sideways, and those aren't in the same direction. In this particular equation, the work equals force times distance, you're going to be using that in two of your problems. One of the problems will be 7.4, and the other problem on your assignment that you'll be using that same equation is 7.6. I'll write 7.4, 7.6, because those are the two assignments that are going to use that equation. Now sometimes the work is done at an angle. For example, in this particular case where we have a suitcase. So here, the suitcase is moving in this direction. Only the force that's in this direction can we count. So even though this is the total applied force, I can't use that whole force. I can only use this part of the force. And since that is the adjacent side, we would use cosine. So the equation that we can use if something's at an angle is FD, which is your work, times cosine of theta. And you have one of those on your assignment. It's 7.12. And that one's going to have one where it's at an angle, and you're going to have to use that cosine. Now work can be positive, which means part of the force is in the same direction. Work can also be negative, meaning the force and displacement are in opposite directions. That would be where you might have the force this way, but the object is moving this way. So that would be negative work. For example, if I lift something up and I just pick it up and then I lift it up, the force and the direction moving are the same, so that'd be positive work. However, if I have a barbell and I try to lift it up, so I hold it up over my head and then I let it down, my force was still upward, but the barbell was moving down, so that would be negative work. We could also have zero work, and zero work means they would be perpendicular, like in this case. So in that case, you don't do any work because they're not in the same direction. Now you can have more than one force, obviously, like if you have a frictional force. In that case, in order to find the work, we have to use the net force. So it's possible that you might have to find your net force first, then times d cosine theta. And this net force would be if you had, for example, 15 newtons this way, and maybe we had 3 newtons this way, then your net force would be a total of 12 newtons that you would use in there. So sometimes you're going to have to use that FD cosine theta. Alright, a lot of times when we look at work being positive or negative, we look at whether the speed increases. And if it's positive work, the speed increases, and if it's negative work, then the speed will decrease. And 718 on your assignment is going to be using this, where you're looking at whether the speed is increasing or decreasing. Now, the work kinetic energy theorem relates work and kinetic energy. That's why it's called work kinetic energy theorem. It says the total work done is equal to the change in kinetic energy. So my total work is equal to, there's my delta, change in kinetic energy, and kinetic energy is 1/2 mv squared. So if we just have kinetic energy 1/2 mv squared. So to find the change, I would do 1/2 mvf squared minus 1/2 mvi squared, where f is your final and I would be your initial. And 7.2 and 7.6 on your Chapter 7 assignment will both be dealing with this equation. Now, we can also look at a graph. If we want to find the work that's done by a variable force on a graph, we look at the area underneath the curve. So we could look at the position. Let's say this position was 50 and this position was 10. And let's say this force was 0.3. If we wanted to find the work that was done, the difference between these would be 40, we'll say that's 40 meters, times our force, which was 0.3, because again, we're taking force times distance, and that would be my work. And you are going to have one there, you're looking at a graph, and the area underneath the curve, and that one is 7.35 on your assignment. So you have to find the area underneath the curve. And if you had such a thing as maybe there was another force here, this area, if you wanted to find the total work done, you'd have to find the area in this part and the area in this part. And if you had another section here, you would have to find out the area in this part. So work would be the area underneath each section. So we could find the area just for this one, or the work in this section, the work in this section, the work in this section. If we wanted to find the total, we would add all those up. Okay, we can also look at the work that's done by a spring. And spring being like we had a weight attached to our spring. And we talked earlier about Hooke's law, F equals kx. K was our spring constant, and x was how far it was stretched from equilibrium. So that means if we wanted to take force times distance, this would be my force, and then I'd have to take it times the distance that it moved, which would be another x. And so for a spring, that equation that we use is 1/2 kx squared if you want to find the work. And that it's a half because if we think about the area underneath a curve, that's what work would be. We would have to be taking 1/2 because it's a triangle. So for spring problems, you're going to use that 1/2 kx squared. And you have some spring problems. 7.32 is a spring problem on your assignment where you'll be using that equation. Okay, and the next topic is going to be power. Power tells us how fast work is done. So to find power, we take our work divided by our time. And work is joules, time is seconds. So the unit is a joule per second, or we call that a watt. And in case you were thinking about horsepowers in terms of work or power, 1 horsepower, there's a conversion factor there, is 746 watts if you needed a conversion factor. But work divided by time. That also means, since work is force times distance, it could be force times distance divided by time. And force is also equal to m times a, or you could think about this being g, if we're doing acceleration due to gravity. So sometimes it would be m times g times d, where this would be the weight times the distance, and then divided by your time in seconds. But all of those are work. Could also be your change in kinetic energy, since that's also work. divided by time. And you have 7.42 on your assignment, and the other one is 7.46. And both of those are dealing with this equation where you're looking at power. And one probably reminder here, I know on your assignment one of them asked for the time in minutes. This time is in seconds. So that means if you solved for your time and it would be in seconds, you would have to change it to minutes in order if they wanted it in minutes. Okay, another equation that we can use for power, I told you it could be F times D, where this is work divided by time. If we just kind of put that D over time all by itself, that's velocity. So power is also equal to force times velocity. And that one you would be using in 7.62. You would be using that equation. And this force would again be like a net force. And I believe in this 7.62, they give you a mu k. And in order for you to find the force is going to have to overcome friction. And we had last time that frictional force is mu times your normal force. And your normal force, remember, is that support force, which is mg. So you'd have to take the mu that was given to you times your mass in kilograms times 9.8. That would tell you the force of friction, and that would also tell you the amount of force that you had to push in order to get the box to move. So the force of friction and the applied force in that case would be the same, because that's what it's going to take to move the box. So in that particular problem, you're going to have to find that frictional force, and the frictional force is the force that you're going to be using in the problem. So that's kind of a review of Chapter 7. The next couple slides have all the equations on there. And here's your kinetic energy one that we talked about. And then we have the spring and power, and that would be the end of Chapter 7.